processes to positive emotions in relation to self and environment through yoga, biofeedback, complete engrossment, which is reading, listening to music, watching movies, playing golf or bridge, which stimulates neurocircuits of relaxation and pleasure systems and inhibits stress circuits in the mind brain axis. This has been proved by PET scan, and there are several anecdotal reports available. A positive foot, the brain, to conclude, an environment communicate interactively in bidirectional manner. This emerging knowledge offers possibilities that should eventually give us an unprecedented ability to engineer changes in brain, what we call as brain revolution for happiness, longevity, and spirituality. Neurologists, of course, in an excellent position to scientifically initiate this process of brain revolution. Thank you very much.
Now I invite Sudhir R. Jain. He is scientific officer in Bhabha Atomic Research Center, Mumbai, a professor at Homi Bhabha National Institute, Department of Atomic Energy, and adjunct professor at UMDA Center for Excellence in Basic Sciences, Mumbai.
Fine. So I am going to speak on the nature of determinism and time. And this is an old topic, very old topic since the genesis of science. Now what I want to start with is the idea of determinism, and then I'll go over to time. And I must actually accelerate because of managing the time. When we talk about determinism, so we look for determinism first and then we go to time. Now, when we talk about determinism, we have the following things. The laws of physics aim to explain observed phenomena, and our main outcome of all the analysis we perform is actually predictability. If we can predict to greater and greater extent, then we are successful. In physical theories, we need to predict exactly and also try to reproduce our results. And for this description, broadly speaking, there are two levels of description. There is a macro level of description, which is governed by what is called classical physics, which is the idea coming from Newton and Galileo to Maxwell, and before quantum mechanics came in, which is about the micro level of description. When you talk about micro level of description, we are talking about atoms, nuclei, and small, very, very small scale objects. And then we have a quantum mechanical description. Now, what is the end of all this is that there must be a deterministic outcome. And I want to actually talk for a moment, for a few minutes, on the nature of determinism. What is the nature of determinism in classical physics, of classical description? Now, it is well known that a flutter of a butterfly can alter the weather prediction of a distant place. And that is a quote from a very celebrated paper by Edward Lorenz, who is the father figure of the subject of classical chaos. This hyperbole, however, captures the unpredictability that is inherent due to the fact that the equations that we have, which I don't want to stress you with equations, I didn't write equations here. The equations that we have are essentially nonlinear. When we say nonlinear, I still want to venture into to telling you what is nonlinear. Nonlinear is something when response is not proportional to cause. When the response is proportional to cause, then we are talking about a linear theory. Now, all the descriptions that we have of nature is completely nonlinear. So the experiments as simple as coin toss, as you well know, if I toss a coin, you can never tell me whether it's going to be head or tail. So I know that it will be head or tail, but in a given toss, you can't tell me that it is head or tail, and you can never do so, in fact. And so there is a simple system, a coin, which I know everything about the coin. It's a circular disc. I can give it some energy. It goes up, spinning, and comes down. I can still not tell if it is going to be head or tail. And therefore, we invoke probabilistic approach. Therefore, the classical determinism, which was there until the beginning of 20th century, took a grand turn due to the advent of the theory of chaos and nonlinear dynamics, and this brought it very close to the philosophical tenet of Syatvad of Jainism. And so the nature of this determinism in classical physics is very closely equivalent to Syatvad in Jain philosophy. In quantum mechanics, it's even more interesting. quantum theory proposes that there is no degree of localization that you can have for a given system. So there is a wave-particle duality, and this means essentially that I am forced to come to the following experiment, that we all have seen waves created on surface of water of a lake or a pond, and we see that these waves interfere and produce very intriguing pattern. We also know that light interferes, but what quantum mechanics proposes is that electrons interfere. Now you can say that electrons are very small, so okay, electrons may have some wave-like behavior. What about larger objects? Now, 15 years ago, Anton Zeilinger in Innsbruck showed that if I have 60 atoms of carbon, which is called fullerene, a large molecule which has the shape of a football, not the size of a football, the shape of a football also interferes. If such a macroscopic object can be made to interfere and shown that its position can't be specified exactly and must have wave-like behavior, then we have to think about larger objects. We as humans are not excluded from this, although the behavior is very hard to observe, but in principle, we are not excluded from this. And quantum theory, therefore, encapsulates in itself the idea of anekantvad, because for a process to take place, even if I drop this pointer, I'm not going to do it, but if I drop this pointer, there is a path that you will see that it takes, and it takes a certain time to do that, and it follows a certain path. But according to the quantum theory, actually it can take any possible path which you may feel is completely unphysical and absurd, but the fact of the matter is, I must include all the contributions of all possible so absurd looking paths in going from this point to the bottom of this floor to actually predict which path it takes and what is the possibility of this process to take place. Therefore, even quantum mechanics, quantum mechanics tells us that there is a probabilistic sense of understanding. So when we say we have a deterministic theory in physics and in science, we still have to invoke probability. And in this sense, truth, therefore, is probabilistic. Truth is at the end of a probabilistic process, which is exactly the philosophical tenet of anekantvad in Jain philosophy. Therefore, the most important ideas in classical and quantum theory, that of determinism, are actually deeply connected with Syadvad and Anekantvad. Now I come to the point of time. Time is a very deep concept. To tell you what I want to do, I want you to play a game. And this game is set up on this ring. You see, the ring has a certain sides which are 1, 2, 3, 4, etc. up to n. If you don't like n, you can take it as 10 or 11. And then there are balls in between these sides. So there are red balls and green balls. Now, what is going to happen is that there is an evolution. There is a game we are trying to play. At each time step, we are going to move all the balls one step to the right. One step clockwise. So this one goes here, that one goes there, and so on. Okay, this is how it is. The arrangement of balls, the colors of balls taken initially is random. Now, each time step, this comes here. And so that's a very simple dynamics which is going to occur. Except that now I introduce that a slight twist. The twist is that some of these sides are marked by this blue star. So what happens in this game is that if you cross this blue star, the color of the ball changes from green to red, or red to green. So red will go to green. And now we start the game, and the game is that we will keep, at each time steps, move these balls around this ring, and we are going to ask you at a given time how many red balls and how many green balls. And so it sounds, like a very, it's not appropriate to talk about games in such a serious kind of conference. But the point is that this n can become as large as 10 to the power 100, and the conclusion of the game will not change. And therefore, it will be very intimately connected with the idea of time, as I will come to. I want to convey my idea through this game because I have a limited time. I have something important to say. Now, if RT is now what will happen at the next time step? let me say, put some figures here. So R as a function of time is given by number of red balls, G of t is number of green balls, and there are small r of t is the number of red balls just in front of the marker. So these are going to turn green, the next step. And G of t is the number of green balls in front of the marker, and these balls are going to turn red. Now, so what's going to happen? Next time step, I have few little steps, and I have to have two equations. I'm a theoretical physicist. I have to prove that. So I have two equations here. And so at time step t plus 1, the number of red balls will be the number of red balls at previous time plus the greens which will turn red. And I will lose the red balls which were before the marker because they will turn green. Right? Is that kind of understood by everybody? Right? That's great. And similarly for the green balls, because that's all the maths I need. Okay? And the number of fraction of sites which are marked is, let us say, some x. That's some fraction, out of the 10 to the power 100 sites which are there, some fraction is marked. And now I start this game. Now you see, if I go once around this whole ring, the dynamics is that there are total n sites. After n times steps, n times steps. After n times steps means all the balls have gone one full circle. After all have gone one circle, because there are n sites, and after n steps, all have gone once. If all have gone once, all the colors will change. All the reds will change to green, all the greens will change to red. So there will be a complete inverse colors of what we started with. And if I go again, one more n time, I would get the whole configuration back. So I'll get the entire very complicated configuration of 10 to the power 100 balls back exactly at the same state where I started. What I'm talking about is that there are two fundamental issues of time. In Jain philosophy, there is the nature of time is cyclic. And in science and also in other philosophies, the nature of time is linear. In science, we believe that according to the second law of thermodynamics, all the systems evolve in such a manner that there is a thing called entropy, which is a measure of disorder. And I'm not going to say anything more. You just can believe that it's a measure of disorder. And it's basically a quantity which tells us that if I leave a system alone and let it go to equilibrium, then this quantity will go on increasing continuously with time. And when I'm talking about time and how it is going to change, I need a quantity. I can't say that time changes with time. I'm trying to see what is the direction, what is the nature of time. So I have to have a quantity with which I compare. So in this case, this quantity that I have is entropy. In physics, it is entropy. The arrow of time is the direction in which entropy increases. Now, this quantity is most important because this is at the second law of thermodynamics. All the systems and happenings in the world follow second law of thermodynamics. And this tells us that if I start a system, it is going to evolve and entropy is going to change. So the direction of time is identified with the direction of entropy. Now I show you, I'm nearly at the end of my presentation. If for the game that I showed, which was a ring of balls, which is also a large complicated system, because at any given time, the configuration of red and green balls is extremely complicated. And if I take this example, we understood that in 2 times 2 n steps, in n steps, all colors become opposite. In n more steps, they will be restored because opposite of opposite is the same. Okay, so they will restore. If you start with a configuration, you come back to the same configuration. It means that the entropy, and this is a scientific work published in a very respected journal 3 years ago, that if I take this entropy, now here is entropy as a function of time, entropy increases and actually goes on becoming constant, so the system is in equilibrium, and then after some time it starts to come back and is completely restored, and therefore for this system it is scientifically shown that entropy is a cyclic function of time, and therefore if I understand the motion of time as the direction of entropy, then we have an exact example. This is exact is a very important word. This is exact with no approximation. And there is no one who can challenge. This is an exact example where I show that entropy is a periodic function of the recurrence time. And the recurrence is guaranteed because our universe is finite in extent. This I mentioned yesterday also. So I come to conclude that universe is finite in extent, and therefore, thanks to a mathematician called Henri Poincaré, recurrence is guaranteed. But this guarantee only is such that the entropy increases with time, and arrow of time is only one way. But if we have now produced an example which shows that recurrence can be exact, then we have in fact shown that entropy is a periodic function of recurrence time, which is exactly the point of view that we have in Jainism with the cyclic character of time. Nevertheless, at each local epoch in time, the entropy increases, but locally there can be processes where entropy has cyclic nature in time. And I conclude with the conclusion, therefore, that we have time as a cyclic character. We have shown that this is not in contradiction with science, because we did a calculation in science. Okay, and so to conclude the first part, the classical and quantum determinism is very much within the philosophical tenets of Snellvad and Anekantvad. I have finished my talk, and thank you very much.
Now I request Dr. Krishnaswamy Natesan. He is former professor of English, Central Institute of English and Foreign Languages, Hyderabad, and currently emeritus professor, Jain Vishwabharati Institute, Ladnu. He is a doyen of English teaching in India. Presently, he is working as an educational consultant in Bangalore. Dr. Natesan.
Good afternoon, everybody. I am a total outsider here, because quite a few delegates asked me, what are you doing here? So I would like to first of all thank Dr. Mishra, the chairman of the conference, and the Vice Chancellor of Jain Vishwabharati University, with which I am associated, and also Samani Chaitanya Prajnaji, because I am also associated with the Mahavir Institute, Mahavir Center. Maybe as an outsider, total outsider, because I am not a scientist, I am not a Jainologist, not even a Jain, I would like to present a different point of view, maybe more objective. See, the word science itself is a borrowed word. We have borrowed it from via Greek and Latin root. Once you borrow a word from some other language, we borrow all the concepts and the methodologies along with the bag and baggage, everything we borrow. We don't have a word for science. Sometimes this word, Vigyan, is used, but in the Upanishads, Vigyan is used only for intellect. Annamaya Kosha, Vigyanmaya Kosha. It is used for intellect or buddhi. Probably the closest approximation for the word science is Shastra. That is the closest approximation. Or Vidya perhaps. Now when I say our ancient knowledge systems are far, far superior, much more ancient than all the Western knowledge systems, people might say you are glorifying only yourselves. It is only self-glorification. So I have quoted in my paper from a very interesting book by Dick Teresi, a well-known American science writer. He has written a book on the lost discoveries, from Babylonians to the present day, with a lot of documentation. I will just cite one or two examples, because I don't have the time. The organizers say I must finish within 12 minutes. I don't know how they arrived at 12 minutes. The Babylonians developed Pythagoras' theorem 1,500 years before Pythagoras was born. But the West grabbed it and they have given the name of this theorem as Pythagoras theorem. Secondly, Indian mathematicians performed multiplication, algebra, geometry, and even ventured towards calculus. They created a place value system and created the number 0, which is Purnam, or sometimes Shunya. Once Albert Einstein remarked, we owe a lot to the Indians who taught us how to count through the decimal system, without which no worthwhile scientific discovery could have been made. And Dick Terzi also quotes another a mathematics writer, Maurice Klein, a prominent historian of mathematics, who says, Indian mathematicians are fools. And he also says in that book, the achievements of Egyptians and Babylonians are just like the scrawling of children learning how to write. This is how they debunk other knowledge systems. Macaulay, in his infamous Minute of 1835, he says all the knowledge that you have in Sanskrit and Arabic will not equal even one shelf of European literature. And he further says,